hot? Nope, it's not getting hot. That's not good. It won't change much if I don't make it get hot. Okay, so the easiest way to trap gases is the way we trapped them, by bubbling through water. Right? We want to catch that butane in order to make sure it was sealed. We made sure we bubbled it through water so we could direct where the bubbles went to. The water made a great seal. So in that container, the pressure in the container is going to be caused by the gas collected and by the vapor, the water vapor. So when we said the pressure inside our flask full of butane was the same as the pressure outside, the pressure was the same, but it wasn't all butane. Some of it was water vapor. So I really should have subtracted the water vapor from the total pressure. Because gas plus water vapor equals total pressure, so if I subtract total pressure minus the water vapor, it tells me what the pressure of the gas actually is. Because we can pretend like the water vapor and the other gas don't affect each other at all, because these are still ideal gases. Okay? So you just need to know the pressure of the water. Well, to find it, you go to table A8 on page 899. And there you will see the vapor pressure of water at various temperatures. It's a table. It's starting to warm up good. So this is what it looks like. The table looks like this. Okay. So in this room right now, so let's look at the scale. Oh, come on. I want a little. 899. There we go. So if we look at the scale there, it's first row is temperature in Celsius, then I got millimeters of mercury pressure and kilopascals. Okay. Can do it. Okay, so in this room, we're at about 19.5 degrees, because that's what our thermometer said, right? It said 19.5, so we can expect the vapor pressure of water to be 17 millimeters of mercury, or 2.27 kilopascals. So you can just look up the vapor pressure of water. Now, technically, what if it was 17.3? Well, you'd have to do an interpolation between those two. And since it's 0.5 here and 0.5 there, 0.3 here should be 0.3 there. That makes sense? But if you look at the numbers, as the temperature starts getting higher, those vapor pressure numbers get higher and higher. So at 22, we're up to 20. Did it again. Come on. Make it easy to serve. Not too far. Okay. By 30, it's up to 31. By 35, it's at 42. By 60, it's 149. So from 30 to 60, it more than doubled. Okay. And then 70, it's 233. 80, it's 355. 90, it's 525. And at 100, it's 760 millimeters of mercury, or 101.3 kilopascals. So what's special about 100 degrees Celsius? What was 100 degrees Celsius? What was the definition of 100 degrees Celsius? When water boils, when there's 1 atmosphere pressure. What's the pressure of the water vapor when water boils? 1 atmosphere. Okay, because boiling is making bubbles. Isn't that what boiling is? To make a bubble, you got gases. And if you're going to make a bubble underneath the water, you have to lift the water out of the way. Right? Because if you blew a balloon up in a beaker, the water would rise. Well, just like that bubble is steam, has got to push the water up. And when it pushes the water up, it's got to push the atmosphere up too. So it can't make a bubble unless it's pushing hard enough to lift the atmosphere. So things boil when their vapor pressure equals the external pressure. So that's why if you pick up a box of macaroni and cheese, there's 3 sets of instructions. There's stovetop instructions, microwave instructions, and high altitude instructions. Because if you're at high altitude, your pressure's lower. And if your pressure's lower, it's going to boil at a lower temperature. Because at 90 degrees, you get 525. If you live someplace where the pressure's 525, your water's going to boil at 90 degrees Celsius. So in Denver, a mile high, they've got lower pressure. So the boiling water they're cooking with isn't as hot. Because you can't get the water above 100, because as soon as you try to turn it above 100, it goes away. So to boil that water in Denver, the water's colder, so it doesn't cook the food as well. So you got to cook your food longer at high altitude. Gets to the point at the top of Mount Everest, when you get down to about 65, it boils at 70 or 65 degrees Celsius, which is not enough to kill germs. So mountain climbers, when they get to the extremes, can't take food you have to cook, because cooking doesn't do any good. It doesn't kill the germs, and it doesn't get hot enough to really cook. See how that would happen? So that's why, so they run into a problem of they have to, you light a fire. First of all, it doesn't burn very well because there's less oxygen around. But when it does burn, it heats it up until it boils, but that boiling water's not hot. So it's a challenge. Now let's go back to our okay, so we're starting to go up in temperature. And we got a blue line and a red line. They were right on top of each other before, right? Now there's a bit of separation. Okay. Let that go, continue on. Okay. We'll come back to it. Hopefully it'll work for us. Okay. So, sample gas is collected by water displacement. The atmospheric pressure in the room is 757 millimeters of mercury. The vapor pressure of water is 17 millimeters of mercury. What is the partial pressure of hydrogen under these conditions? Was this number 10? Oh, nope, the wrong one. It's 11. Number 11. So this would be a lot like what your lab should have looked like. The pressure you should have used for butane should have been not the room pressure, but the room pressure minus the vapor pressure of water, which would make your pressure lower. And since molar mass is dRT over P, you're dividing by a smaller number. So your molar mass will be reported higher, which 95% of you, your value is too low. You need it to be bigger. If I use a smaller pressure, I'll get a bigger answer because of the way it's arranged. But this is pretty simple. Equation, well, let's look and see. They told me one pressure, they told me another pressure, and they want another pressure. Well, P1 is the total pressure, right? So P1, P total, has got to equal P2 plus P3, not P. So that P3 equals P total minus P2, which is 757 millimeters of mercury minus 17 millimeters of mercury, which is 740 millimeters of mercury. So you do a simple subtraction, and then you use that as the pressure of that gas. We're talking about how many moles of gas it is. Because you shouldn't use the total pressure if it wasn't all the same moles. So if I want the moles of hydrogen, I need to use the pressure of hydrogen. Hey, really tough? See how this is just like the homework? We're just getting our number from a table in the back of the book. That's where I got that number. I looked it up. So, 12. Oxygen gas is collected over water at 25 degrees Celsius and a pressure of 1.02 atmospheres. The total volume of the gas collected is 293 milliliters. What volume of oxygen would be collected at STP? So that gave me one temperature, one pressure, one volume. They want a second volume, so that must have been the first, and those other two must have been first pressures. You want V2, and you tell me STP, and that's another temperature and another pressure. They're okay with those? STP is another temperature, another pressure. And there's another place. Remember, those are defined quantities in STP. They picked a cold room, and if they picked it exactly. They're not going to pick something close to 0 degrees Celsius. It's got to be 0 degrees Celsius. And, oops. So, hey, anybody know equation with all those pieces in it? Well, it would be P1 V1 over T1 equals P2 V2 over T2. And I want to solve it for V2. So V2 is going to equal P2, oops, sorry, wrong side. It's going to be P1 V1 over T1. And then I got to move the T2 up top and the P2 to the bottom. So I'm ready to plug in numbers. So what is the pressure of the oxygen? What? The pressure of oxygen, is the pressure of oxygen 1.02 atmospheres? That's the total pressure, isn't it? If I want the pressure of just oxygen, I've got to have the total pressure minus the pressure of water, vapor pressure. So that's going to be 1.02 atmospheres minus, and now I need to look up, the water was 25 degrees Celsius. So I go look up 25 degrees Celsius, and it says it is 23.8 millimeters of mercury. But I can't subtract 23.8 here. Everybody see why I can't subtract 23.8? So I got to take that 23.8 millimeters of mercury and change it into atmospheres. 1 atmosphere is 760. So 23.8 divided by 760 is 0.031 atmospheres. So 102 minus 0.031 atmospheres is 0.99 atmospheres. So the VT would be the 0.99 atmospheres times V1, 293 milliliters. Now, we have been forced to change it to liters, but that's because we were using R, and R had liters in it. Are we going to use R this time? Nope, so I can leave it in milliliters. My temperature 2 was STP, so that was 273 K. My temperature 1 was 25, which is 298 K. And pressure 2 was 1 atmosphere. And a few of you on the homework thought of that as 1 sig fig, but it's got to be unlimited. Just like the 760's got to be unlimited, the 1's got to be unlimited. It's a definition. They picked a room. So you push those buttons, and you get 0.99 times 293 times 273 divided by 298 equals 266 milliliters. And it should be pretty close to the same because the temperature went down, so you'd expect less volume, but the pressure went up, but we expect a little bit less for both of them, so, but not a huge difference. Now let's check and see how our graphs are looking. No, they're not the same, right? So the blue one has higher pressure. Why? Because it doesn't have just air in it. Start off with air and some liquid water, now it's got air and more water vapor. Okay. And you notice the red line's pretty straight. The blue line's not straight. So it's related, but it's definitely not a direct relationship. One goes up, the other goes up, but not the same amounts. That make sense? Okay. So we'll come back to that later as the temperature keeps going up. Okay, and here's another application of Dalton's law of partial pressures. So you got 2 containers connected by a valve. One holds 4 liters of nitrogen at 2 atmospheres. The other holds 2 liters of oxygen at 8 atmospheres. The valve is opened. What happens to the pressure of the nitrogen, the pressure of the oxygen, and the total pressure? What is the pressure of nitrogen, the pressure of oxygen, and the total pressure? So I've got 2 containers. Got a valve, I open up in between. The oxygen molecules are going to move over towards the nitrogen container just randomly. The nitrogen molecule is going to move over the oxygen. They don't get in each other's way because they don't have any size and they don't have any attractive forces. So they just mix together because they're moving randomly. So what's going to happen? Now, if I just asked about the nitrogen and the other container was empty, all I'd be doing is changing the size of the container. If I'd asked just about oxygen and the other container was empty, all I'd be changing is the size of the container. So I've got them bouncing around separately, and when I open up the valve, it makes it so the molecules are going to mix. Okay? So how are we going to do this? Well, we're going to be able to pretend that they're completely separate from each other. So for the oxygen, what was the first pressure? Actually, let me do it on the correct side. Now, what was the first pressure of the oxygen before I opened up the valve? Okay, the first pressure it had was 8 atmospheres. And its first volume was 2.0 liters. What is volume 2? Well, when I open up the valve, how much space does the oxygen have to move around now? It can now move in 6 liters, right? So that P2, I should be able to solve for, because the temperature didn't change, and this is a sealed container. I didn't talk about the temperature changing, sealed container. So I should be able to use P1 V1 equals P2 V2, because I can cross out the temperature off the bottom. combined gas law without temperature, or Boyle's law. So P2 is P1 V1 over V2, or P2 equals 8 atmospheres times 2 liters divided by 6 liters. And if I do that, I get 2.33, I get 8/3. And with 2 sig figs, that's 2.3 atmospheres. It makes sense that it's 8/3 because I've got 3 times the volume, so I should have 1/3 the pressure. Make sense? So that's the pressure of the O2. What about the N2? Well, for N2, the same thing was true. P1 was 2 atmospheres. V1 was 4 liters. V2, the oxygen has the same 6 liters to move around in. So what would P2 be? Well, P2 would be, well, I've already done the equation over here, so I can just reuse it, that it would be 2.0 atmospheres times 4.0 liters divided by 6.0 liters. So P2 is 8 over 6, which is 8/3. 8 over 6, no, it's 4/3. 1.3 atmospheres. So the oxygen pressure is going to drop to 2.3 atmospheres. The nitrogen is going to drop to 1.3 atmospheres. And what is the pressure total going to be after I open up that valve? Well, it's going to be the pressure of nitrogen plus the pressure of oxygen, which is 1.3 atmospheres plus 2.3 atmospheres, which is 3.6 atmospheres. So all we did was pretend that the nitrogen didn't have to worry about the oxygen. I opened up a valve into an empty container. Pretend that the oxygen didn't have to deal with the nitrogen at all. I open up the valve to an empty container. Treat them completely separate, and then I can put them together. Yeah. Oops. Well, I guess we're done collecting data. Man, what happened? Well, pressure got high enough that it popped the popper off. So, actually, let's do this instead of versus time. Should be able to change that axis. Oh, I got to stop it before I can do that. Okay. So instead of this axis being time, let's do temperature, and let's change the scale. Okay. So there's our data. When you blow it up, it looks a bit different. So the vapor pressure here had to be the difference between this and that. That difference is the vapor pressure. Okay. And notice the one with just air is a straight line. V over T. That's all we changed. This one changed because the number of moles of gas wasn't constant. The hotter I got the gas, the more could escape. So the amount of gas kept building. So I got more molecules moving faster, which is not going to be a linear thing. And they don't. You watch how that vapor pressure grows. They start coming off faster and faster. So this curve would accelerate. I just wasn't willing to go all the way. So let's go back to Amy's question, though. 2.6. Did I do badly? So on pressure of oxygen, so 2 times 8 is 16. Divided by 6 is 8 divided by 3. 8 divided by 3 is, 2 2/3, so it should be 6. You're right, 2.7, because you do 2.66. And that changes my answer to, instead of 4.0, it ends up at 4.0. Now, I don't know if you recognize this, but what we really did right here is take the geometric mean. It's the geometric mean. Not the arithmetic mean, but the geometric mean. You learned about it once and then forgot about it. This is geometric mean. Multiply the two together, multiply the two together, and add. Okay. So, that showed you a little bit about the pressure of water. Now I want to show you a little bit about the pressure of the atmosphere. So, we don't feel it right now very much. Oh, but it's there. The atmosphere's there. Because I blow up this balloon. It didn't blow up very far, but that was intentional. What's making the balloon this size? Okay. What's making the balloon this size? Well, it's got 3 factors. We usually forget the third one. The first one is that there's air molecules inside bouncing around. Okay? Hitting the inside of the balloon, making the balloon bigger. The balloon takes some energy to stretch. So the pressure in this balloon is a little bit higher than the pressure outside because the balloon is squeezed in a little bit. So I got to fight the stretch of the latex. But the other thing I have to fight is there's molecules outside the balloon hitting. So the molecules inside the balloon have to be hitting hard enough to stretch the balloon and push the atmosphere out of the way. So the total pressure in here is atmosphere plus stretch equals what's inside. The atmosphere collisions plus the stretch of the balloon has got to equal how hard they're hitting the inside. So what I'm going to do, I need one more beaker. Okay? What I'm going to do is I'm going to put it underneath that bell jar. And that bell jar is hooked to a pump, a vacuum pump. Okay? So what this pump has inside of it is a piston. Okay? And that piston goes back and forth. So it opens up a valve from inside the valve opens up from inside the bell. Then it closes. The piston pushes that air out, comes back, opens the valve again, the air from inside comes in. Close the valve, push it out. So all it does is push the air out over and over again. And you find the on switch. Okay. And then you open up the valve. See if we got a good seal. Doesn't feel like one. Hey, so the balloon's getting bigger. Why? So what did I say I was doing inside the bell jar? I was taking air molecules and they're moving out. So now there are fewer molecules hitting the inside than the outside. There are fewer molecules hitting the outside than the inside. So fewer molecules, less pressure. Yeah, that's what I had. Had turned wrong, valve turned the wrong way. Okay, is everybody worried about it popping? Because you're worried about that loud noise? It wouldn't make any noise. All you would hear is the rubber balloon hitting the bell jar, because to conduct noise you have to have air. Yeah, what can you do? Okay, so if you walk in, so go into the office and come through. and right in front of the elevators.
Just in front of the elevator.
Yeah, right next to the elevator. So you got to go into the office and then go out through the other door.
Okay.
So if it popped, the only air was that little bit of air inside the balloon. That's all that could conduct the sound. So that's it. So now you notice I got a straw here. That's so because if I don't put that straw there, it seals here and then sucks it down to the plate. So the balloon got bigger because there are fewer molecules hitting it. Okay. Now, how hard is the atmosphere pulling? Well, let me show you. This base right here, probably weighs about 40 pounds. I can't pull it apart. Fact is, in the 1800s, what they showed to show the pressure, the power of that air, they would take two hemispheres and suck the air out from in between them, and then attach the hemispheres to horses. And the horses couldn't pull the two hemispheres apart. It holds stuff together really hard. Our atmosphere is pushing on us really hard. We're just used to it. Because when you let the air back in, oops. Okay. So another demonstration I want to show you of those same ideas involves a little bit of water in my flask that I'm going to boil. Because I'm going to boil some water here. Is that too much? That'll be fine. Excuse me. Oops. Helps if you open up the right jet. Okay, so that water's going to boil. Now I'm going to take this second beaker and fill it up with water. And so you can see where the water is. Oh, look! The outside of my flask is covered with water. That's the water from combustion. Okay, so then it's going to start to boil. I want to put a little food coloring in here so you guys can see where the water's at. Ooh, yellow's a lovely color. What I had handy. And I'm going to stir it up a little bit. Okay. So, when I boil this, the water vapor is going to form at the bottom, and then it's going to actually fill the whole flask with water vapor. It's going to push the air out as it makes water vapor. The air is going to be pushed out. And the flask is going to get full of water vapor. Come on, we can't watch it. Watch. Come on, you can get hot. I put too much water in. It doesn't take that much. So the water's going to boil. Watch it. There we go. And I want it boiling so I make sure that I pushed all the air out of there. Okay, now that it's boiling, and it's boiled for a minute or two, okay, I can be pretty sure that that's all water vapor. Then I'm going to put this so that water vapor has to go up the tube. And I've got water vapor coming out the tube at the top. So this flask is full of water vapor right now. And now, missed it. All right. Now I'm going to let it cool off. And as it cools off, it takes up less room. I now have a flask full of water. How did the water get in the flask? How did the water get in? Well, when I first flipped it over, what was the pressure inside the container? Well, the pressure of the atmosphere, right? And that pressure was caused by the gas molecules. What kinds of gas molecules were in the flask? Water vapor. What happens to water vapor when you cool it? Well, it turns back into liquid on the outside of the flask, right? We saw it turn water vapor the water vapor turned to water on the flask, so that water inside must have turned into water vapor, must have turned back into water. And if it turned into water, how much gas is left? If the water vapor in here turned into water, what's left inside the container? Well, what was in it before I flipped it over? Water vapor. If that water vapor turns into water, what's left? The correct answer is nothing. There is nothing left in the flask. And how hard does nothing hit? It doesn't hit. There was no pressure in the flask. There were molecules outside the beaker hitting the water, though. So the water could go someplace where it wouldn't be hit. It got pushed up the tube by the air. This air here pushed it up the tube because there was nothing pushing back. So this is what's holding this up is the same thing that would hold up that mercury in a barometer. That the air hitting here is hitting hard enough to lift water that far. Water, it could actually hit to lift it 30 feet. Yeah. You might want to think about it. Oh, you mean I'm trying to tie it all into that tanker? This is all going to tie into that tanker, guys. We started there. We're going to end there. It's coming back. Okay. So there's that. All right. So I want you to practice a few of these. So I'll give you about 20 minutes. Then we're going to come in and talk about the second half of the day, and I've got some more demonstrations to show you. Okay? So the homework for tonight starts off on page 329. But since you don't have a book, I took the time to do this. Well, it went away. Here's my super suit. Okay, let's make it bigger so everybody can see it, because I'm going to have to put the table on the other screen. So, sorry, question there, table there.